Okay, what's going on, guys? So today we are going to be talking about general relativity. I know I put a pause on general relativity for a while. We're going to pick it back up and we're going to get to some advanced stuff in general relativity. We're going to try to come at it from a very first principles perspective, keeping in mind that we've talked about a lot of pretty advanced stuff up until this point. Last time we stopped on talking about the Schwarzschild metric. That's going to be the stepping off point for what we're going to do next, which is going to be the Kerr metric, and that's going to come next week. Before we dive into the material here, though, what I want to mention is that I do have a website coming out soon. Right? I'm trying to accelerate the process. The website is going to contain I'm sort of in the process of transferring videos to the website, making it look nice, making it look pretty user-friendly as well. And on top of it, a lot of the videos are going to switch over to not being me writing on the board, but I'm going to start incorporating more and more animations as well. I'm teaching myself animations with Python, Samson, Blender, and all these interesting, very nice software programs that help in facilitating really interactive looking nice animations. And so I'm gonna do that. So that's there. I have the animations, I have the website in the works, and hopefully that's going to come out soon. Another thing with the website is going to be online tutoring. Okay, I really love teaching. I really love learning new things and then communicating those things to you guys. And so what I aim to do is online tutor, right? The online tutoring is going to be sort of specific at first. I'm more comfortable with chemistry, general physics, electromagnetism, some of the more advanced stuff that we've been going through, like Chern-Simons theory, conformal field theory, I'm comfortable with, but I'm still sort of getting into the swing of things on those, trying to figure out how I want to work on those if it comes to tutoring with those. So right now, I'm just keeping it at a very general basis, trying to help you guys again ace your classes, right? If it's med school, if it's undergraduate, if it's a master's, if you have a course in your PhD that you're interested in wanting to do really good in, then I'm going to be there for you. Okay, so that's something of a detour on the website, everything that's going on the background of this channel. Let's go ahead and talk about general relativity and talk about where this playlist is going to go. All right, so this playlist this is really outlined right in this diagram here. This is kind of a messy diagram, but we're going to go through this. This is going to be what the next probably many weeks is going to be, right? So I'm going to start off by just sort of recapping what we've done up until this point, because I know it's been a while since starting general relativity. So we talked about the metric tensor, right? That was a long time ago. The metric tensor is this thing that we can put everywhere on space. So we have some space-time, and everywhere on the space-time we can put something called a metric. Okay, and then that metric can change in time. So that metric can change in time. That metric can change in space. But everywhere in this manifold M, there is a metric. Okay, and that metric has x, y, z, and t coordinates, and it's usually expressed as a matrix. Right, so this matrix thing is located here, and then so that's our metric tensor. Okay, so that's just a brief overview of the metric tensor. The affine connection then comes from the idea of changes in the metric tensor. Okay, and it enables us to compare 2 points, to vectors at 2 points on our manifold together between each other. Right, so if we want to compare two vectors or two scalars or two tensors between 2 points, we use the affine connection to do that. Okay, and that incorporates derivatives of the metric tensor. We also introduced this idea of p-forms. We didn't go too deep into it because p-forms will show up later when we talk more about advanced stuff in general relativity. But we'll keep that in the forefront of our minds as well. We sort of talked more about p-forms when we were talking about Chern-Simons theory, and because Chern-Simons theory really uses the idea of these forms where we're going to understand something like this, where A is the electromagnetic field tensor, and so we're not really totally going to look at p-forms in the context of general relativity quite yet. And then we talked about the covariant derivative. The covariant derivative is where things really got interesting. The covariant derivative was essentially what the derivative in the most general sense. It's a directional derivative in the most general sense, and it is we call it a tensor. Okay, the covariant derivative along some direction v of some metric. Okay. And so that was the covariant derivative. That the covariant derivative told us something about how these things change along some direction, right? So the affine connection enables us to compare two adjacent points. The covariant derivative is going to enable us to tell us what the derivative is of some object at some point on the manifold, okay, in some direction, right? Because you need to specify the direction for that. Then we sort of talked about the Lie derivative. The Lie derivative was sort of this offshoot of the covariant derivative, and it's important in telling us something about the nature of the manifold itself. When you parallel transport some vector here, and you go in this direction, say, and then what the difference is if you go in this direction, okay? So it's the difference it'll tell something about the difference in the vector, in some vector or some object as we travel in two different directions along some closed path, all right? And that's going to lead us to something called the torsion tensor. Another tensor that we got was the Riemann curvature tensor. And the Riemann curvature tensor is not what you get when you compare to a vector when you go sort of half circle like this, but what the difference in the vector when you go full circle, right? So if you have some manifold here. I'll just copy a manifold, and we have some vector, right? So here's our vector. Well, when we parallel transport this vector, we parallel transport here, and then we go this direction, and then we go this direction, then we come back this direction. If for some weird reason our vector is different upon going through this motion, then this is an indication of curvature, and the difference here is the degree of curvature in the manifold. Okay, so and that's the Riemann curvature tensor told us that's the sort of what that degree was, whereas the torsion tensor again really compares half circle. So if you get a vector that you parallel transport this vector here, and it ends up looking like this if you take this path, but if you take this path, it ends up looking something like this. That difference is going to tell us something more about the torsion tensor. All right, so we have torsion tensor, then we have the Riemann curvature tensor, and then we sort of left alone this idea of the torsion tensor and put it sort of in the back burner a little bit. And we typically what happens through a general relativity course is everything becomes sort of shoots off from the Riemann curvature tensor. This is really the basis of general relativity. Everything prior to it is almost like prerequisites. And the Riemann curvature tensor is really where everything begins to offshoot from. And the first thing you normally talk about is the Ricci curvature tensor. All right, so the Ricci curvature tensor is a contraction of the Riemann curvature tensor because there's a lot of indices in this tensor that are symmetric Okay, and so we can get rid of a lot of them. Because we can get rid of a lot of them, and when we get rid of a lot of them, we end up with this compacted Ricci curvature tensor. So the two are the same, almost one and the same thing. They tell us something about the curvature of the manifold. One is just much easier to deal with because it has less indices. Okay, and then from there we contract even more. Okay, with our metric tensor, right? So we contract our Ricci curvature tensor, because again, at every point in space-time, we can construct a Ricci tensor. We can construct some Ricci tensor at every point in space-time. So like right here, mu nu. Well, we can also construct at the same point G mu nu. G mu nu. And when we contract these two things, well, we get the scalar curvature. The scalar curvature is written as, I'll do blue, R, just R. Right, so Riemann curvature tensor is going to be nu mu alpha beta. And then a contraction of that is going to be the Ricci curvature tensor. That's going to be R mu nu. And then the scalar curvature is just going to be R. So we're contracting these indices. There's symmetries in the Riemann curvature tensor that leads us to the Ricci curvature tensor. And then contraction of the Ricci curvature tensor with a metric is going to give us the scalar curvature. And then we sort of use this idea of Ricci curvature tensor and scalar curvature tensor to then tell us something, to then construct something called the Weil tensor. And the Weil tensor is the traceless part of the Riemann curvature tensor. So again, if you think of a matrix, for example, a matrix, for example, is going to have these elements such that you can calculate the trace of the matrix. You can calculate the trace of a matrix, but then there's the traceless parts of the matrix as well. And the traceless parts of the matrix are going to be the Weil tensor. The trace parts are going to be the Ricci tensor, because the Ricci, again, there's symmetries. There's going to be a lot of symmetries here. Everything that's not a symmetry, that's going to be part of the Ricci curvature tensor. So the Ricci curvature tensor and the Weil tensor they're almost opposites in the sense that one is the trace of the Riemann curvature tensor, and the other one here, the Weil, is the traceless part of the Riemann curvature tensor. This tells us something about how shapes deform as they travel along geodesics in space-time. Okay, the geodesics will pull, and they'll pull on objects as the objects travel through space-time, and that pulling is described by the Weil tensor. You could sort of think of it in that way. Okay, and so there's all this. So we haven't gone. There's this whole rabbit hole that you can go down, which we will, when we start talking about the traceless part of the Weil tensor, and we start incorporating it with scalar curvature, and we start also incorporating it with Ricci curvature tensor, and all these things. If we combine them in some unique, interesting way, we get new and interesting tensors that we can classify in certain ways. And these tensors, some of the more interesting tensors, these are going to be, this is sort of this rabbit hole of conformal invariance. These interesting tensors, they're all going to tell us something about how things are, they're all going to parse out, if you will, parts of the Riemann curvature tensor. This all comes back to the Riemann curvature tensor, parts of the Riemann curvature tensor that tell us something interesting or something unique about how things change when we have conformal invariance involved. And conformal invariance is this idea that when you have a conformal invariance is something that's invariant upon a conformal transformation. A conformal transformation is the most general transformation we can think of. We've talked about conformal field theory, right? In conformal field theory, you can do all these interesting things to to your frame of reference and maintain the physics, right? If the physics is maintained under these weird deformations of your coordinate system, then you have these things are conformally invariant. These aspects of the physics are conformally invariant, and a lot of these aspects are going to be encapsulated in these various different types of tensors. So we have the Lanczos tensor, we have the Cotton tensor, the Bach tensor, Schouten tensor, and we can all classify these in different ways. That's going to be called Petrov classification. And so this is one rabbit hole we can go down. Another rabbit hole we can go down is, well, we talked about the Einstein tensor, right? The Einstein tensor was related to the Ricci curvature tensor, and this sort of gave us, once we implemented the Bianchi identities, then we were able to get the Einstein field equations. And the Einstein field equations, we needed to know something about T mu nu, right? So T mu nu is not the Riemann curvature tensor, it's not the torsion tensor, it is a new tensor. This is the stress energy momentum tensor, right? And so this is where the physics comes in. This is sort of the big guy in general relativity. This was, right, you had R, I'm going to decrease the thickness of my pen here. You have R, mu, nu, G, mu, nu, and then R. Actually, I'll just do it like this because I don't want this to become too busy, and my pen thickness is too small, I think. You had the geometry is proportional to, actually, I kind of like the thickness of my pen there. Let's do the geometry, which was encapsulated in R mu nu. More specifically, actually, big G, right? So that this is the Einstein tensor, is proportional to the stress energy momentum tensor. That was the Einstein field equations, right? This is really the Einstein field equations, the idea that geometry is affected by physics. Okay, and then there's a couple of rabbit holes now we can go down with here. And these rabbit holes are going to include many very, very interesting aspects of general relativity. And these very interesting aspects of general relativity, we've kind of gone down one of these rabbit holes already. One of them was this formulation, Lagrangian formulation for general relativity. We kind of went over this already, and then that sort of deep dove us into the electromagnetic stress energy tensor and the Raynaud conditions. Okay, we talked about these guys already. These are just the conditions that have to be met in order for there to be electrophysiology incorporated into the Einstein field equations. Well, from the electromagnetic stress energy tensor, we can also talk about Newman-Penrose coordinate systems, and these are going to be. This is also an attempt to incorporate electromagnetic stress energy tensor into general relativity, and there's going to be connections between this and conformal invariance. Okay, and so that's why I have this dotted line here connected to this conformal invariance rabbit hole. Some interesting things that we haven't really gone into are a Hamiltonian formalism for general relativity. We kind of gone over this in talking about quantum gravity, but not totally in depth yet. But we can really go into depth on this. There's a lot of stuff we can go into depth here. We talked about the Pelletini action a little bit. We haven't really. This was in our quantum gravity playlist, and we'll pick that up as well. The Nambu-Goto action as well for string theory. All of these guys really dive us deep into quantum gravity, which is its own separate playlist, okay? And then there's this red rabbit hole. This is kind of interesting. This sort of goes all the way back. This sort of ties into quantum gravity as well. But I made this its own rabbit hole because there's this thing called de Sitter and anti-de Sitter spacetime that I think would be very it would be very, very interesting to go down this rabbit hole, but it's not the next rabbit hole I want to go down yet, because there's a few things that I want to go over before we talk about de Sitter and anti-de Sitter spacetime. Primarily because I kind of just want to get them out of the way, but also primarily because I am this is kind of an advanced topic, and I think it sits on the heels of going over some of these well-known metrics before we get into this. But once we understand de Sitter and anti-de Sitter spacetime, which really is going to have to do with cosmological constants, and that's why I have it attached to Einstein field equations here. Then we'll be able to understand thermodynamics. And once we understand black hole thermodynamics, we're going to get into the ADS, which is anti-de Sitter spacetime, and CFT, which is conformal field theory. And we're going to find a correspondence between the two. And this is really this ADS CFT correspondence is really a hint towards quantum gravity as well. But the next rabbit hole we're going to go down starting next week is going to be looking at not all the metrics, because there's more metrics than just the Kerr metric, Kerr-Newman metric, and Reisner-Nordstrom metric. These are just sort of the big guys when it comes to talking about black holes, charged black holes and spinning black holes. So you have the static black holes, you have the spinning black holes, you have the static charged black holes, and the spinning charged black holes. And those are the four types of black holes that are typically gone over after you go over the Schwarzschild metric, right? So the Kerr metric is going to be, so the Schwarzschild metric is static, Kerr metric is rotating, Kerr-Newman metric is, sometimes I get these mixed up, but these two are going to incorporate a charge as well, right? So you're going to have spinning no charge, spinning charged, okay? Spinning charged, I believe, is the Kerr-Newman metric, but I don't quote me on that. I can't remember what goes with what, but we are going to go down this rabbit hole starting next week, starting with the Kerr metric. We're going to really beat this guy up, and then from the Kerr metric, we're going to do the Kerr-Newman metric, and then we're going to do the Reisner-Nordstrom metric at the end. And so that is where we're at. So what the plan is going to be this rabbit hole first, and then I think I want to do this rabbit hole next, and then we're going to revisit the Weyl tensor. We're going to do this rabbit hole next, and then we're going to do this rabbit hole next. But primarily we do this one closer. We're going to do this one sort of last, because these tensors are very abstract and very weird. So so that's how that's going to be, right? So we have conformal invariance is sort of going to be the last thing. We sort of primed ourselves ready for that. And so this is ready to go in the back of our minds now. We're going to do this, get these metrics out of the way, and we're going to do this rabbit hole. All this over here, the Hamiltonian formalism for GR and ambiguous action palette, these are all going to be in a separate playlist, which is quantum gravity, and that is on the channel already. We're going to come back to that playlist because I sort of put a pause on that as well. But with that being said, this is all of general relativity in a nutshell. There's more to it, right? There's a lot more to general relativity than just this. But this is where we're at, and this is where we're going, and we'll add to this later. And so with that being said, make sure to hit that like and subscribe button. Keep an eye out for any announcements that I will come out with regarding my website and all that. And I'll see you guys in the next video.